can come up. Yep. You can see the oxygen coming up in the ozone lines, and all of those are really fingerprints in the spectrum that you can get out. Of course, because of the coordinating. Yep, give a notification. So you can really see the fingerprints of all those materials in the atmospheres themselves. What we also found was that ozone and oxygen is really best visible in the UV. There is some discussion still around this. Can we see the oxygen bands at 700, 800 nanometers, or do we really have to go to UV to see the ozone band that is also produced when you have oxygen in the atmospheres? Finally, what you might think is, well, doesn't transit spectroscopy give you the same kind of information? It also gives you the atmospheric abundances of each of the chemicals. And the answer is that it's really the combination of those both that provide completely separate information. Transit spectroscopy really probes the low atmospheric pressures really high up in the atmosphere, while the direct imaging spectroscopy probes all the way down to the surface of the exoplanets. So even if you were able to get both transit spectroscopy and direct imaging spectroscopy on the same planet, you would get different information. You would constrain different parts of their atmosphere in there. Of course, being from Leiden, I cannot not mention polarization. So we also want to see polarization on these exoplanets. We want to see some glinting of the sunlight on any water surface, big oceans that are there. We want to see Rayleigh scattering in their atmospheres, probing down different molecules. We want to see rainbows, right? Rainbows are very, very polarized, and we want to see those as well. They are completely different spectral polarization structure, and we might be able to see those in there. Glories are another thing which we don't really think we can see. If you look on the left, you can see a view of the observer looking at the planetary system with colored bands, which polarization components are in different parts of the field. And glories are just way too close in to really see for many systems. So how many systems? Well, here is a plot from a submitted paper with how many of the Habitable World's target list, how many planetary systems we would be able to see these polarization signatures in. So on the top, you can see the inner working of the coronagraph in lambda over d, the diffraction width of the star. And you can really see that you need to get really, really close in. Think 2 lambda over d, 3 lambda over d for these kind of signals, including full 10⁻⁻⁻ performance at that level. If we want to see polarization signals, we really need to go that close in. So how do we get that close in? We do that with a coronagraph. So here's an example coronagraph by Bernard Liot in 2039. Of course, we have come a long way, but basically every coronagraph shows a similar structure. So it's instructive to go through this. So normally the PSF from a star looks something like on the bottom left. A telescope pupil has a certain point stress function that is determined by diffraction. And the diffraction is really, really strong. Think 10⁻⁻3, 10⁻⁴ in the first 5, 6 lambda over d, which means that we need to suppress it. And of course, the simplest way is just to put a black dot on the star. You don't have the brightness of the peak of the PSF anymore, but you haven't done anything to the outside at all, right? You're just blocking the center part. You're suppressing any light that is outside of that focal plane mask. What Bernard Liot discovered was that we can put a second mask in the pupil afterwards. So going back from the focal plane to the pupil, you can see that all of the starlight before that Liot stop is pushed outside of the pupil of the planet, the telescope. So that means that starlight, you can suppress that. You can put a mask there that suppresses all the light outside of the pupil, while you're not doing anything to the light that goes inside that Liot stop. So finally, what you get is something like this. You get your coronagraphic PSF on the top that is much, much deeper than the PSF itself. You really get that optical suppression that you're looking for of these types. Of course, if you look at the color bar, bottom is at 10⁻⁶. Real coronagraphs don't work like that. Real coronagraphs are much deeper. So how deep do we need to go? Well, these are all the known exoplanets by transit method or by radial velocity. and computing what the planet-to-star flux ratio is for these kind of planets. Also labeled are the different diffraction limits for ELT, VLT in the optical to show kind of how deep do we need to go. So most of these are Jupiter-like planets, and for a solar-type system, we really need to go much deeper than this. So normal Jupiters, hot Jupiters, are all at 10⁻⁷, 8, 9 level. Our Jupiter would be a 10⁻⁹ planet at 10 parsecs, and Earth would be a little bit closer in at 0.1 arcseconds, really at the 10⁻⁻10 level. So that's how deep we need to go. Of course, to design such a coronagraph, you need to do extensive calculations on how that coronagraph performs and how emission with that coronagraph would perform. So this is a typical output of a yield simulation formed by Chris Stark, showing how what kind of planets would be discovered with, well, you simulate a full mission with a set of coronagraphs, and you see which planets in a simulated universe would be observed and detected and characterized with that mission. So these are luminosity distance diagrams with the colors showing the coronagraph that detects the planet and the coronagraph that actually characterizes the planet afterwards. And I'll come back to this later on. So in response to habitable worlds, HICAT started a few working groups, and here are the 4 working groups that were started this year. And these will be providing roadmap information for like what coronagraphs to prioritize, how do we decide what coronagraphs to prioritize, where do we think as a community where the money should go, and all those other things that are important for roadmap development. So I'm part of these 2 working groups, especially the third one, which is dedicated for surveying which coronagraphs are out there, how far each of those coronagraphs are in their development, and what chance they have to get to TRL5 to really demonstrate them in a test bed in a reasonable environment. Can they get the performance that they claim they can do at the actual telescope? So this group will be creating graphs like these. This is a graph by Russ Belikov in 2019, where he showed the fundamental limit of coronagraphs on the bottom right. We know where our fundamental limits are. We also know that our designed coronagraphs for real apertures, all the stars in this diagram, are not at that fundamental limit. And we want to get closer to the bottom right of this plot for any of our current designs. So some coronagraphs, here is for LUVOIR-A, basically all those coronagraphs on a line for the LUVOIR-A aperture. With the simpler the aperture gets, generally the closer you can get to that line. So here's LUVOIR-B without a sense obscuration that apparently makes coronagraphs a lot easier to design. And the most simplest aperture that we can think of, a circular aperture by HABX, can get even deeper. So generally, there is a gap for improvement. There is nothing theoretically that prevents us from going deeper towards that theoretical fundamental best performance coronagraph. For any aperture of these apertures that I showed here, the coronagraph fundamental limit basically doesn't change. So what Russ proposed in his paper was that in the future, when we get better with coronagraph design, we might actually get closer to that fundamental limit. And that turns out to be true. So in the years afterwards, papers came out for the PA Vortex and for the PA-PLC that I will be talking about today that are chronograph designs for LUVOIR-A, so the top line, but they are much closer to the fundamental limit, with the PA-PLC basically having the same performance as the best current designs for HABX, a much simpler aperture and much easier to design for. So we can break that trend that we used to have. We are now starting to break that in chronograph design. I want to also say I'm a developer of HICAT, which is a chronograph and adaptive optics simulation package. So all the simulations that I've been doing over the last, basically my whole career, have been using HICAT, and HICAT has been open source now for 5 years. It has been used in 100 papers since then, so it has really taken off. And it has been adopted by many institutes around the world so far. Every time I give this slide, I have to put in 1 or 2 more institutions, which is really nice to see. So HICAT can do everything from winter and halo simulations, so that's the atmosphere moving across your aperture and your adaptive system responding to that, to using algorithmic differentiation for chronograph optimization on the top right. This is showing a fully general chronograph being optimized by this method and basically reaching the same performance as all the other chronographs, to actually optimizing the current manufactured chronographs for GPI 2.0, which is a exoplanet imager on the Gemini telescope. We manufactured these optics, we did all the simulations and optimization with HICAT, and we are now getting ready to install them in the GPI Notre Dame and get them on SKY for the first time, again, because it's GPI 2.0. So the Phase Apodized Pupil Lyot chronograph, right? I told you that breaks the current limitations, but how does it work? So it basically follows the same structure, general optical structure, as a Lyot chronograph, but instead of having nothing in your pupil, you now have a phase apodizer. So on the top left, I'm showing the phase apodizer there, and in the next focal plane afterwards, you apodize that PSF, you create a dark zone on one side of the star, the right side here, and all the light is basically pushed from the right side to the left side of the star. By itself, this is not very deep. This is a 10⁻⁵ dark zone, so it's not traditionally good for exoplanet imaging, but that is not what it was designed to do. So what we do instead is not look at that first focal plane. We put a focal plane mask there. We put a dark knife edge there that blocks all the bright side of the star, including the core of the stellar PSF itself. So you're left with like 10⁻⁶, 10⁻⁵ light. However, in the next pupil afterwards, you can see that all the light has been pushed outside of the telescope pupil itself. And it is much, much tighter, much stronger emission than the Lyot chronograph that I showed before. So of course we can block that. We remove, again, more than 99.9% of the light. And what we end up with is a dark zone on the right side of the star, which has an inner work angle of 2 λ/d, so really, really close in, high throughput, think 80% plus throughput, goes all the way down to 10⁻⁻⁰, all the way out to 32 λ/d for this specific design. So these are really high performance chronographs, except for, as you might have noticed, it only looks on one side of the star, right? So if you need to look for planets, if you want to detect planets, you don't know where they are, then you need to do multiple exposures at different position angles to really find where it is. But once you found it, you can characterize the hell out of it. You can really get high throughput spectroscopy of these planets, basically at down to 2 λ/d inner work angle. So we did a simulation early on for a chronograph for LUVOIR-A. Can we get better performance than the baseline mission so far? So again, this was done by Chris Stark based on yield packages that I supplied to him. This is a baseline mission for LUVOIR-A with 4 different chronographs, 3 APLC chronographs and 1 vortex chronograph. And what we did was we replaced one of the vortex chronographs with a PAPLC. So basically look at the red points. There's a few red points now. Changing that chronograph to LUVOIR to a PPLC, you can see that we get a whole extra row of detected exoplanets basically on the border of detection, and all of the chronographs are now being characterized by the PPLC. Note that this is not something that we put into the optimization. The optimization by Chris really finds the best chronograph for each planet separately, and this is showing that the PPLC is really chosen for every characterization observation that there is. So showing them next to each other, you can really see the stark difference of that whole extra row or band of extra planets that you find with the PPLC. In the end, we find about 25% more exo-Earth candidates for this specific case. Of course, that's still to be confirmed with better simulations, with better inputs to that U calculator code. So given that we saw very good performance, we tried pushing this for ground-based telescopes as well. So I did some designs for Sphere Plus, which is an improvement on the current Sphere instrument on the VLT, where we are currently trying to push for an adaptive optics upgrade, but also chronograph upgrades, because you can have as good of an AO system as you have, but if you don't have a chronograph that can take advantage of that better stability, then you might as well not have the AO upgrade in the first place. So we did I'm doing DM offsets on as the phase appetizer. It's not pure phase, but it's close enough for ground-based. And we found very semi-achromatic solutions. So think of J and H band in a single shot, 50% bandwidth in a single image. These solutions were also a very high throughput, more than 60% relative throughput, and especially in inner working angle, we can get down to 1.6 lambda/d. So I said that they were achromatic. Here's a chromatic contrast plot with a black line showing the average of all the spectra, and the other colors showing different monochromatic propagations through that chronograph. So you can really see down from basically 1.5 to lambda/d, you already get below 10⁻⁶ performance for the chronograph itself, excluding adaptive optics performance there. Throughput is also excellent, so 64% relative throughput, 40% of the light goes into the core of the planet, and the inner working goes really 1.6 lambda/d, as shown in this simulation. You can also see that it's very sharp rise. It's not a very smooth curve going from 0 to the maximum. It's a very sharp rise and then a slow asymptotic relationship afterwards. And that is very much in contrast with other chronographs that operate that close in. Other chronographs are really, really slow to rise up. The APLCs and POPLCs are really much sharper than other chronographs in that case. So showing the PSF to show morphology, it's just a single spot that comes up from behind the focal plane mask, and the white line here is the edge of the focal plane mask. So you can see there's pretty much just a spot of light that comes up outside of that. Of course, if you don't simulate the atmosphere, then you're going to get wrong deductions from that data. So what we did was we collaborated with the Saxo Plus team, which is doing the AO system upgrade, and we simulated their AO system with this chronograph. So on the left, you can see the current chronograph that is installed on Sphere. You can really see all the speckles that are clearly visible by eye. This, with the AO system upgrade, the current chronograph will not cut it. You will not get much better performance, maybe a factor of 2 better, but the AO provides much, much better performance than that. So on the right, you see the image with the PPLC chronograph design, and you really see just the AO background. There's very little speckles in the dark zone left. By the way, dark zone is on the right. So any planet on the right will be visible, but the left side is behind the knife edge. So don't be confused by the contrast being very good there. So just AO backgrounds basically in the dark zone, which is very, very nice for that chronograph. And we're still now trying to push them to, well, if you are going to do an AO system upgrade, clearly you need a better chronograph as well. Otherwise, you're not going to gain the advantage that you got from that better AO system in the first place. Showing a angle separation contrast plot for all the different chronographs that we investigated. The red line is the PPLC chronograph, basically asymptotically being the same as any of the perfect fundamental limit chronographs, the perfect chronographs, and getting much better performance than basically all the other chronographs that we investigated on Sphere Plus. Of course, we're all not here to talk about ground-based. I think most of you here are space-based people. So when I joined Space Telescope in 2021, I wanted to get this chronograph on an actual high-contrast imaging testbed to really test its performance, not at the 10⁻⁶ level, where it's important for ground-based, but really go down to 10⁻⁸, 10⁻⁻⁻, for space-based chronographs. So this is I did that research on the HICAT testbed, the high-contrast imaging imager for complex aperture telescope testbed, which is a testbed meant for system-level demonstration of the high-contrast imaging systems. So that means target acquisition, being able to deal with different mirrors, trying to flattening all of them, trying to get an image, basically fully automated structure. There's a lot there that is not as clearly demonstrate it with just component level demos. You really need to do a system level demo to demonstrate that you have a full system that works, not just a single component that works. So this is a system diagram of, or an optical diagram of HICAT with a light source on the bottom right, light cascading through the entire system, hitting the first our segmented deformed mirror. So this is a deformed mirror where we have control over each of the individual segments. We can drift the segments. We can see how our system responds to that. We have the complication of flattening that segmented mirror in addition to flattening our DMs. So that's system level demonstration. We have two continuous deforming mirrors to have both phase control and amplitude control. The first one does phase control, and the first and second one together can do amplitude control as well. And you really need both to get the performance that we are after for a space telescope. Next, the focal plane mask of that. I forgot to mention. The apodization that we do are on these DMs. So we are using the DMs as our apodizer, as our phase apodizer there. The focal plane mask, we use a very, very simple right angle prism as our knife edge. So the light that hits on the right side, hits the face of the right angle prism, gets reflected and goes to the Lyot stop. The part that's on the left gets transmitted, so you won't ever see that again in your chronograph image. The Lyot stop, I don't have an image of it. It's a simple circular mask. So apparently in the 4 years that we've been working on this, we never bothered to take a single image of that Lyot stop. Something I want to rectify. So it's simple circular mask for this, even though we have a very complex aperture, all the segments. It's not, our Lyot stop is still simple, and we're trying to rectify that as well. So in since last year, we've been rewriting all the software. Our problem was that we could run wave control, but we could not run it fast enough to work with the area in our system. HICAT is an in-air test bed, which means that there's still internal turbulence that you need to suppress, and going faster is always the better thing to do with turbulence. You don't want to spend minutes on a single iteration. You want to spend less than a second on iterations. So you can really stabilize, freeze out that atmosphere while you're trying to suppress that. So we rewrote our entire software system to take advantage of that parallel loops, trying to really push down in speed. And in the end, this software enabled, and it's not showing up on the screen. It is now. This control loop really demonstrates or enables fully asynchronous control loops. We can really operate a low order loop at the same time as a high order loop, completely at the same time, with no interaction, no problems from a software perspective at least, in operating those loops. On top of that, we achieved around 240 times faster loop speeds on this system. So we can now really start to freeze down that atmosphere. We are not limited by atmosphere anymore, at least on this, for the sensing part of our control loop. So I want to be a little bit technical here and try out the things the problems that we encounter when going faster, right? You can go faster, but you encounter limitations of your system, and one of the limitations is that you think you send a command to the deformable mirror to actuate a certain DM map, but the DM will take some time to get there. And on top of that, your images that you take will not show that change immediately when it happens. It will also need to read out the images, transfer it over to your computer, have the computer put it in memory, all those things that take time. So this is a timeline from left to right, with the DM command being issued at a certain time, and then DM replacement happening a certain time later. So here is some numbers for that. There's some processing time for our software. There is communication of the controller card with the actual DM, and then there's the DM response time. The DM also takes a little bit of time to move that actuator to the position where it's supposed to be. During that time, the camera is taking images, different exposure times, and shown here is the start and end of each of the different images. Afterwards, the images need to be read out, which takes a little bit of time, and then communication from the camera needs to happen to your computer, needs to have some processing done on it, and then at the red line is where that frame is actually available for the computer to use for its control. So what we define as latency here is starting from when you send the DM command from your software to it actually appearing on your cameras sometime later. Experiments that we do for this is kind of give data like this. So this is showing the sum squared difference between subsequent frames. So you look at your image, you send the DM command, and you look at how does that image change over time. Each of these points is a separate image, and I'm tracking when the time between that frame and the time of sending DM commands. So from this, we get a latency of about 2.2 milliseconds. Very, very short, but you need to worry about that if you want to send commands at 100, 200 hertz on that camera. So what we actually do is we send a DM command. We still take one last camera frame because we are still guaranteed to not have that second DM command on there. We then wait for a little bit to have that DM command actually appear on our cameras, and then we continue our measurements. So this is really about synchronizing camera frames with DM commands while you're doing the control to freeze out the atmosphere here. So does this work? Here's a comparison of before our software upgrade, or at least our old software and our new software. So this is run on the same day, just literally an hour from each other, showing that, yes, going faster actually helps us get down in contrast quite a bit. On top of just being able to run more experiments in the same time, right? The left showing 80 iterations in about 2 hours time. On the right showing 500 iterations, more than 6-7 times as much in only 15 minutes, meaning that you can do 8 times more experiments in the same amount of time. You can really brute force things that you would otherwise have to spend your own mental effort on trying to solve. You can now brute force that in a night rather than spend a day of your own time on trying to learn something from very sparse data. So this really helped us explore so many different parameters that we were not able to explore before. We also, of course, didn't do software upgrades alone. We had a team of undergrad engineering, mechanical engineering students at Johns Hopkins work on improving the enclosure. So on the left is the enclosure before, and on the right is after, and I think you can see the difference. It's not just a visual difference of all the cables being gone, or at least consolidated into pipes. It's also that this removes any of the gaps in our enclosure that we had. So we had air coming into our bench, creating extra turbulence. This now basically eliminates all that air gap and really reduces the amount of turbulence. So some more pictures showing the awful clean room compatible tape that is actually not clean room compatible at all, apparently after like 2 years of use. And on the right, showing completely clean plates, which were completely made new, and all the cables and clamps coming out of to keep things stable. We also tracked down some of our vibration sources at the same time, so they went through the entire setup, tracing an incoming vibration from our wall throughout the system, acoustically and mechanically vibrating the mirrors inside, and we tracked it down. And we eliminated that chain of vibration transmission there. So we now are not limited by vibration anymore. We're now limited by chromaticity and actual things that we are interested in studying. Phasing primary mirror is also important. We have a factory flat that comes from a piezo interferometer for our default mirror. And on the left is an image with that PSF. That's not clean enough for us, so we did all the phasing as well using differential optical transfer function phase retrieval, and we got the image on the right. So much cleaner, basically stabilized to about 1 to 2 nanometers RMS on the modes that we can actually correct with that mirror. So extremely tight performance, optical performance for that specific element. And then we put in the apodizer. We put in the apodizer on the default mirrors. We dig a dark zone. And these are the results for the PPLC with that whole infrastructure chain coming together. So on the left, monochromatic performance, 2 times 10⁻⁸ performance from 2 to 13 lambda over d. So really showing 10⁻⁸ performance at that inner working of 2 lambda over d, and showing the progression towards broadband images with a 25% image on the right, showing just below 10⁻⁷ performance, all the way from 2 to 12 lambda over d. The outworking was slightly reduced there because you now need to control the same, or effectively larger outward angles for the shorter wavelengths that you're controlling there. 25% is the largest bandwidth that that the high-contrast imaging community has done so far. So this really puts the PAPLC basically on par with other coronagraphs in this respect, at least for an in-air testbed there. To show that the throughput is not just blocking the planet altogether, which is the easy way to get contrast, showing the core throughput of the planet as function of angular separation with and without the apodization on the coronagraph. So you lose basically a few percent of throughput when you put in the coronagraph or versus without. And the apodization has very, very little influence on the actual coronagraphic throughput there. So this is showing the exact same as our simulations, completely conform to everything that we expected there. The PAPLC, because it's such a simple chronograph, right? You just need an apodizer, you just need a knife edge, which is easy to get, has been explored by other testbeds as well, showing very, very similar performance. So we had performance at the THT2 in Paris Observatory, where we showed basically 2 × 10⁻⁸ performance as well, from 2 to 9 lambda/d. And this was tried on MagEOX as well, with a 5 × 10⁻⁸ with a 3 lambda/d in a working angle, and on Scoop, which is a vacuum testbed in Arizona, where they reached again 2 × 10⁻⁸ from 4 to 11 lambda/d in this case. So PAPLC is not just on HICAT, it's now on other testbeds as well, and has been achieving basically the same performance on all of those afterwards. So I've not talked about wavefront sensing at all, and wavefront sensing is an integral part of why this coronagraph is so important, to me at least, for inclusion on habitable worlds. So this is a PSF for a chronography image for LUVOIR-A, and this is just with the face of the pupil completely flat. There's nothing on the segments. Segments are completely flat. However, we know that that is not the case. We know that this is work by Randall Telfer on JWST, showing that segments actually move. Traditionally, what we were worried about for monolithic telescopes was very low order, right? You expect some very global modes to appear on the pupil. However, for segmented telescopes, that is not the case. We have to worry about segment discontinuities, phase discontinuities across 2 segments. That really impacts high order aberrations. So for LUVOIR-A, I did the simulation, and this is showing basically a short term exposure of a drift of these segments, independent segments, showing that you don't get the contrast that you are looking for in that case. However, you can do something with that, right? You can sense those aberrations as they are happening and try to control them. So result of those simulations is this. You can get much deeper. This is with photon noise included, with read noise, with an actual solution for wave sensing. You can really get that contrast back with active control. That's what we are looking for to do. So how do you do that? Normally, what you would have is a dedicated wavefront sensor for these telescopes. You have a sensor that measures aberrations and tries to correct them before you're even hitting the chronograph. What I'm proposing here is trying to combine those 2 into the same system. So I'm trying to use the light that is reflected by the knife edge chronograph and trying to use that light as a wavefront sensor. So what I did here is you imprint a Zernike dimple, a phase dimple, on that knife edge where the star is, and that means that the reflected light from that knife edge, you can put it on the camera and you can look at that light, and it basically performs as a Zernike wavefront sensor. So normally, when you do that, this was done on HICAT as well for the APLC chronograph, it looks something like this, right? You have the light from a very small focal plane mask. It's basically a low order, low resolution image of your pupil, and you can see the hexagonal shaped outline of your aperture, but it's very, very blurry. So it's very hard to see those phase discontinuities for the segments. You can do it, but it's very, very tricky. For LUVOIR-A, when you want to look closer in, you're going to make this even blurrier than this, and it becomes completely impossible to see the individual segments. However, with the PAPLC, it looks something like this. So much, much sharper. You can see the individual segment gaps even appearing. You can see the print through of the deformed layers, the regular rectangular pattern of spots that you see in this image, you get all that information in your reflected light. And the reason for that is that the knife edge, instead of being very, very small in your focal plane, you now have all the information on the the left-hand side of your image. So you have the full high-order information included in that reflected light as well, at no cost to your chronographic image whatsoever. So putting them next to each other, you can really see that increased fidelity in the high-order information that is in there. Of course, showing this pupil right now doesn't say that there is high-order information in there. So what we do is we imprint Zernike modes on our deform mirror. We try to see how well our Zernike sensor can retrieve that aberration, that sinusoidal aberration on your image. So this is showing it as a function of basically angular separation, increased spatial frequency across your DM, showing that you can get basically in an uninterrupted performance out to 10 lambda over d, which is where this experiment ended. Can we see segment gaps as well? Yes. On the left, you can see segments, trying to move them up by tiny amounts in piston. And what happens with our DM controller is that that's discretized, so you can see them wiggling, trying to push up in general. We can see those discontinuities in raw light. So on the top, you can see how much we're pushing. We're really pushing at the nanometer level, and our DM is slightly misbehaving, completely up to spec, but we are now actually able to sense that while doing chronographic images. On the right, we're putting Zernike modes on that, and polynomial mode basis with higher orders being higher spatial frequencies on the mirror. And you can really see visually that there's no reduced response for those high orders versus the low orders that other chronographs are able to measure. The one very tricky experiment is trying to see the DM discretization itself, right? DMs are discretized, voltages are discretized, so we would like to see that in our actual images. So what we do is we send a DM map, as shown on the bottom right. Every fourth actuator we try to poke up, and we look at the Zernike image when we do that by tiny amounts, when we push up those actuators by a tiny amount. So pushing up by only 20 picometers, that's below the discretization threshold. However, some of the actuators start to respond. They jump up by a full bit in their response. So that means that only a few of the actuators you actually see on your Zernike image, and all the other are basically staying where they were. As you push more and more and more, up to 100 picometers, which is about 1 bit on our controller, you really see now all the actuators try to respond to that poke, and not just the actuators that are close to the edge. So really get very high fidelity images of these deformed mirrors. Noise levels are at sub 10 picometers RMS per pixel. So per actuator, you can get basically 2 or 3 picometers RMS measurement in about a minute of integration time on HICAT. So for those of you in the know, this is very similar to what Gareth Ruane did in 2020. The main difference here being the bottom row by Gareth is doing just dedicated Zernike sensing. There's nothing else in the beam. There's no chronograph whatsoever. While the top one has a chronograph in the beam, it is taking chronographic images at the same time of doing these experiments and maintaining the contrast in that chronograph at the 10⁻⁸ level. So closing the loop, we can track these aberrations. We can see the atmosphere moving, and at a certain point we can start the loop and we can start to stabilize all those modes. So when it comes around, we can see this again. So the low order aberrations that we have, it's still an in-air testbed. We still see atmospheric movement. I'll start it again. We still see that atmospheric movement inside the testbed itself. And when we close the loop, we can measure those aberrations. We can control them on the DM. We can really stabilize all that to about 15 picometers RMS per mode on HICAT itself. Of course, this is only for the slow aberrations, so 10 hertz or slower. For the high speed, we have aberrations in our system that we are not able to control. We can measure them. We cannot physically control them because they're just too quick, which is, by the way, the reason why we went so far in vibration analysis of HICAT, is trying to get that to a level where we wouldn't care anymore with that. Of course, next step on HICAT, the Zernike dimple and the knife edge are on 2 separate substrates. We have to physically align those two substrates together. And of course, that's going to drift over time, so there's some non-conform path there that we have to worry about. So the next step is trying to etch that Zernike dimple in the knife edge itself. Really have that on the same substrate, then basically eliminating the non-conform path aberrations for this whole system, really integrating them into a single optical element. So here's a prototype made by the University of Arizona, a nanofabrication center, where on the left is a photo of the knife edge. The gray part is actually the casing in which this was held, and the gold is the coating applied on top of there. Really high, very, very sharp knife edge there. On the middle is a peripheralometry images of that knife edge dimple, with the knife edge being on the bottom, basically where the ruler is, and showing a very, very sharp, very clean Zernike dimple being etched inside that substrate. On the right is an image where they did that on the MegaUX instrument, showing a lab image with an incoherent source, lab source, showing that this is basically showing a full Zernike response as we expect it to on MegaUX. And this is now going on SCI, where we are getting data from the Zernike sensor while we're doing chronography imaging. I'm still in the process of reducing that data, so I won't have anything to show for you today. But maybe at a later time I can show some of the actual integration there as well. We are getting one of these prototypes as well for HICAT. The manufacturing is slightly different from what was done before. They've gotten a lot better in the manufacturing over the year, so we're hoping that we can get actual high performance chronograph with that substrate afterwards. So to conclude, Habitable Worlds Observatory will directly image and characterize exoplanets with a dedicated high performance chronograph. And I personally see the PAPLC as a promising candidate for this element, especially with its integrated Zernike sensor that can sense high order aberrations, try to stabilize the segments while the dark zone is there and while you're doing chronographic measurements. So I'll leave you with an animation of a true color image of the dark zone being dug on HICAT. So this is exactly as you would see if you would put your eye in the beam over the course of 15 minutes or so, and the segment aberrations being measured by the Zernike wave sensor. Thank you very much. You have to do this one now.
Okay, thank you so much, Emiel. That was really interesting. We have one comment online. That's so cool. Are there any questions in the room? Maybe we'll just pass around this mic that we know is working. I'll start here.
Thanks for a great talk, Emiel. So one of the things that came to light when the APLC was being designed for LUVOIR-A is that there's this trade-off between throughput and outer working angle to an extent that mattered, right? And so when you tried to design a mask with, let's say, a 3 lambda over the inner working angle, you had to reduce the outer working angle to give you useful throughput. What is driving the outer working angle of the PAPLC, and do you have that same trade-off?
Sorry about that.
So for the APLC, the problem is that you need to, instead of pushing the light from the left to the right side, which is relatively easy to do, you need to push it all the way out to the outside of the outer working angle of the chronograph itself. And that turns out to be much, much more stringent on the throughput than you would guess otherwise. So for the PPLC, inherently, that trade-off between outer working angle, you can basically make it as large as you want, basically being limited by the spatial frequencies of your apodizer phase mask itself. There is a little bit hidden throughput if you go further out, but it's extremely minor compared to APLCs. Yeah, so the design for LUVOIR-A that I gave you was 2 to 32 lambda over D. Yep.
Regarding the Leo stop for the PAPLC, I noticed that in your theoretical design, in a way, you are using the outer shape of the pupil and the struts to block the light, but not the segment gaps. Is this something that you tried didn't work, or like there's no point of trying to block that light, or?
The main reason for that was that the struts that we need to cover the segment gaps, they increase the alignment tolerance on that, right? So you need to align that very, very accurately now, and the struts themselves become really, really thin. So I was worried about like some polarization effects from very, very small structures, sub-wavelength effects from that, in addition to just making the stuff harder to make. The reason for the outer edge being hexagonal is that that is actually advantageous for this type of chronographs. The circular mask on HICAT right now, that's suboptimal. Of course, it's making it easier to get these contrasts, right? If you're not that close to the edge, it makes it easier to get the stability that you want. But in theory, you can get better performance if you use some of that extra light and get a little bit higher throughput there, a little bit increased diameter as well, right? You're really getting close to the diffraction limit, so any kind of small gain, 5–10% increase in diameter there helps with reducing that light and getting a little bit more leverage on the phase pattern that comes out.
Since we're sharing a mic, I'll just walk up here with you so you don't have to walk around. I have like a zillion questions from that. There's quite a spectrum of things you just went through, pun intended. But the thing I think would be most beneficial to maybe comment on is the comparison to like David's like VAPP designs and stuff for STScI and the wavefront sensing methods. Because the direction I was expecting you to go with that wavefront sensing was you were going to try to do wavefront sensing around those islands of spots on the bright side. So I wasn't expecting to see the Zernike solution. So I just want to know if, like, comparing kind of what you think conceptually, like top level, what the difference is between those coronagraphs and just the wavefront sensing approach.
Yeah, so there's a lot of similarity between using wave censoring on the bright side, right? It's essentially the same information that you're using there. What is the problem, though, is that that information is only there for if you make your phase pattern asymmetric, and that costs you a little bit of throughput. For a symmetric aperture, your phase pattern will always be, your optimal phase pattern will be symmetric as well, for reasons that I'm not going to go into. So if you do that, then you become insensitive to any all even modes. So you need to introduce some asymmetry in that phase pattern to get that performance back. However, if you use a Zernike sensor, then you don't have that limitation whatsoever. You don't need to introduce that asymmetry there. You don't need. You can also sense closer in than that part. But essentially, you're using the same information for linear dark control or this. In fact, the initial design for that wave sensor was a linear dark control type sensor, and that's when I discovered like you really don't have the sensitivity for the even modes that you're trying to sense.
Got it. Okay, thanks. Were there other questions? Yeah, couple here.
Yeah, I also had like multiple questions. So let me, maybe two I'll give you. So one is, when you simulate with the strut, how big an effect is the strut? Because you can kind of with a half pupil, you can kind of visualize a tripod and a slightly cantilevered secondary that doesn't have any struts. So the question is it worth studying that? And then the other question is just if you compare
The struts, what do you mean by struts?
the secondary mirror support struts. Like in your original predictions, you showed secondary. So imagine if you, I mean, I know you're in the lab not using struts, but from a model perspective, how much does that change things? Like, is it worth the telescope community considering architectures where there's no struts on half the pupil? The second one is if you compare to vector vortex, they claim, less sensitivity to low order aberrations. So how sensitive is this to low order aberrations?
So first about the struts. So the central creation has more of an effect on the final contrast. Just putting that in without any struts gets you pretty much the same the throughput reduction from a design perspective. So the struts themselves, they push a lot of light out for further central creations, and there's some gain to be had with how you place those struts, or rather how you orient your dark zone with respect to your pupil. Of course, you're on a real telescope, you're not going to have any much control over that, right? You cannot arbitrarily clock that telescope however you want. You kind of have to be within like 30, 45 degrees of at least for the sun shield type observatories. So struts, they matter a little bit, but think of the like 1 or 2% level of throughput, not at the 10, 20% level. The second question was sensitivity. So the initial designs that I showed in my original paper were very, very sensitive to aberrations. Even 0.001 lambda over d tilt movements will basically get you 10⁻⁹, 10⁻⁸ performance. Since then, I've included the robustness in the optimization, and I've gotten designs at 2.2 lambda over d in working goal, which is robust to a 0.1 lambda over d star. So really, really increasing that robustness, basically getting a vector vortex charge 6 style of robustness to lower aberrations, not to like the like coma level, but especially for tilt, it's really reduced down to that level. And that's really important for, like, of course, stellar diameter telescopes, a stellar diameter of stars that you look at. Comparable to VPC, maybe a little bit less, like it's a more slope upwards than VPC, which is very, very flat response to aberrations.
Great talk. So I was curious how, in the lab at HICAT, how sensitive are you to the registration of that knife edge? In other words, you have the DM apodization pattern is optimized for one particular placement of that knife edge, but how do you practically deal with the fact that you don't have perfect knowledge of where that is laterally? I mean, do you try to sense that, you know?
That's a very interesting question. I've never had that one before, but it's really important. So right now we're visually aligning that knife edge onto the star. There's no automated procedure for that, so visually maybe 0.1 lambda over d peak to valley tolerance on that. It turns out that it doesn't matter that much where you put it exactly. If you're within 0.2 lambda over d, then it's usually fine. I have to note as well that HICAT, the PSF on HICAT drifts a little bit during that hour that we're doing an observation, and we're not always controlling that. I have not seen that much loss in performance when we do actually control that pointing actively. So typically the PSF moves by 0.2 lambda over d side to side a little bit. It also makes it harder that it's usually side to side that we're seeing on HICAT right now. So it matters. Not as much as you would expect. So basically, being within 0.2 lambda over d, you're usually fine. Of course, initial alignments, right? You need to be directly there, but your dark zone control kind of corrects for that offset relatively quickly.
Let me ask you. So maybe you could educate us a little bit on where you see the contrast being able to get to. I mean, from two perspectives. One is if you keep pushing in air, but you run faster and lower the noise and all that, like, what do you think you can get to? Are you comparing it against a model? Like, can you measure the environment and compare and project? Because there's this overall issue right now that JPL keeps bringing up of, we don't know that we've ever been better than 4 times 10 minus 10. And so the question is, you know, are you going to be able to help address that question? And what's your feeling about, you know, what the prospects are for doing better than that?
So for monochromatic results that we're seeing right now, we are limited by like unmodelable things. So one major term there is DM discretization that I showed that we can measure. Wave control also has trouble getting actually deeper than, I think, 8 times 10⁻⁹ at at the outer regions of the PSF. So at the outer regions, we're definitely limited by that. In the inner parts, we're still limited by some vibration, some model mismatch between the knife edge being on bench and us being able to control it. Of course, that means that your control will spiral inwards rather than go straight in to zero. So the speed of our control system basically would need to be faster, or our model would need to be better to go deeper there. For broadband, we are now clearly seeing chromatic issues that basically respond exactly to what our models tell us it should be with this kind of control that we're doing right now. Theoretically, you can get phase apodizers that take care of that. However, the control is not able to find those in time, which means that we are not able to do it on testbed right now. So the chromaticity is what limiting us in broadband. There are ways to address that, of course, right? You can simulate this on a simulator. You can get an apodizer that works for the simulator, then put that on the testbed and see how deep you can go from that starting point rather than starting from flat DMs. That's what I'm currently doing, and we'll see if that actually is as easy as that sounds or not. My assumption is that it's not that simple. But that procedure that I just told about, that is very similar to what is being done for the hybrid Leo chronograph on Roman. So I think both of us will hit the same issues, or they have already seen some of the issues and worked around it, and that would be helpful to know about afterwards.
If you got this in a vacuum, do you think, or do you think different?
So chromaticity, as the design is right now, on HICAT, we should be able to reach 1 times 10⁻⁸ for a 25% band, given optimal designs. For a 0.1 Lambda-over-D star as well. To reach 10⁻⁻⁰, you need to modify your design a little bit. You need to add a prism pair that we're currently manufacturing as well to put on HICAT to see what technical limitations are for that. And with that prism pair, I have designs that are able to reach 10⁻⁻⁰ at the 2 Lambda/d for basically like a LUVOIR type aperture. The main limitation are the unknowns for that, right? You now have a knife edge which is right across the star, which is a very bright electric field. So there might be some polarization effects that come into that. Polarization might the electric field, magnetic field has to be closed, right? It has to be closed circles. So there has to be some way to go from 0 intensity to the stellar intensity right next to the knife edge. There is some polarization effects there that have not been modeled yet that I am worried about might impact us for the polarization performance. And that will add on top of the polarization aberrations from the telescope itself. Right now, HICAT is operating without any polarizers, so we're using unpolarized light, and our performance is basically the same as with a polarizer in the beam. So we know that there's nothing polarized limiting us at the 10⁻⁸ level, from monochromatic light at least. So we'll see when that turns up. But polarization is one of my main issues there.
So we're at 12, so I guess that's time. I don't see any more questions online. So let's thank Emiel again. Yeah, thanks to everybody who joined online and here in the room. We have another exoplanet seminar on Thursday this week as well, so be aware of that. But thank you, everyone.
We're going to go have lunch now, building